Welcome to In Simple Terms with Satish. I have always believed that the best way to understand technology is by building it yourself. So instead of explaining GPT with another collection of diagrams, I decided to build the smallest working version I could from random weights on an ordinary laptop. And in this tutorial, we are going to build it together. We will turn plain text into prediction questions, build a GPT-style transformer, train every parameter, and inspect both what it learned and where it memorized. Before we write any code, let me show you where we are going. On the left, a language model with random weights. On the right, the same model after 2000 training steps. The prompt did not change. The architecture did not change. Only the weights changed. In this video, we will open the box and trace exactly what happened between those two screens. There is no model API and there are no pre-trained weights. PyTorch gives us tensor math and automatic gradients. We build the tokenizer, batches, causal attention, transformer blocks, training loop, and evaluation. You need basic Python, a laptop, and curiosity. Every claim will connect to real code, a passing test, or a measured artifact. This is not ChatGPT in miniature. It is the smallest useful system for seeing a language model learn. Let's build it. A language model practices one question again and again. What comes next? Computers cannot begin with letters directly, so our tokenizer gives each supported character an integer ID. Those IDs are labels, not measurements. The ID for M is not somehow greater or more meaningful than the ID for O. It is simply an address in the vocabulary. Now take the word model. We create an input sequence called X and a target sequence called Y. The target starts exactly one position later. Given M, predict O. Given MO, predict D. Given MOD, predict E. Given MODE, predict L. A single short sequence therefore gives the model several aligned prediction problems. In code, X slices from start through start plus block size. Y begins at start plus 1 and ends one position later. If Y did not shift, the model would practice copying the current character instead of predicting the next one. Pause here and answer the checkpoint yourself. Why must Y begin one position later? Because the target at every position is the character that follows the matching input position. Now we have training questions. Before building a transformer, we need a simple score to beat. Before adding attention, we build a deliberately limited baseline. A bigram model receives the current character and looks up scores for the next character. That is all. It cannot use a word, a sentence, or even the character from 2 positions ago. Why bother with something so weak? Because a baseline tells us whether the data path, loss calculation, and optimizer are working. In the verified run, this model has only 1764 parameters. Its best validation loss is about 2.31. That is much better than random guessing, but its samples still look like broken fragments. This is useful evidence, not failure. We have isolated the limitation. One character is not enough context. If a more complex transformer cannot beat this score, we know the added machinery has not earned its place. Good machine learning work begins with the smallest comparison that can expose progress and mistakes. The baseline has now shown us the next requirement. The model needs more context, which is the job of attention. Attention gives each position a way to collect information from earlier positions. A query asks what this position is looking for. Keys describe what every available position offers. Their dot products become relevance scores. Values carry the information that is finally mixed together. But next token training has a strict rule. A token may use the past, never the future answer. We enforce that rule with a lower triangular causal mask. Imagine the 4th position in a sequence. It may attend to positions 0, 1, 2, and itself. Every position to its right is closed. If we turn the mask off, the model can peek at characters it is supposed to predict. Training loss may improve, but for the wrong reason. That is, data leakage, not learning. Our test makes this concrete. We change future input tokens and check the output at earlier positions. Those earlier outputs must remain unchanged. A mathematical mask, a behavioral test, and a plain language explanation all point to the same guarantee. Information flows backward through the context, never backward from the answer. We can now combine this safe communication mechanism with the remaining parts of a transformer block. Now the pieces become a GPT-style decoder. Token embeddings provide identity. Which character is this? Position embeddings provide location. Where is it in the context window? We add those representations, then pass them through 3 transformer blocks. Inside each block, causal attention communicates across time. A feed-forward network transforms the features at each position. Layer normalization stabilizes the values, and residual paths preserve a direct route around each sublayer. In code, that structure is wonderfully compact. X becomes x plus attention of normalized x. Then x becomes x plus the feed-forward network of normalized x. The simplicity of those two lines hides many learned matrices, but it does not hide the data flow. Our input shape is batch by time. Embeddings expand it to batch by time by 96 features. The final language model head maps those features to 42 log-mated, one score for every possible next character. Softmax can turn the logits into probabilities. Sampling chooses the next token. Then the new token is appended and the process repeats. The architecture can now make predictions, but its weights are still random. The next step is learning. The model starts with random weights, so its first predictions are poor. Cross entropy compares its get entrotron with the correct next token IDs and returns uses automatic differentiation to compute how each parameter contributed to that error. Adam W uses those gradients to adjust the parameters. We clear the old gradients, call loss.backward, call optimizer.step, and repeat with another batch. Nothing in this loop contains English grammar rules. The structure emerges because many small updates make the observed next characters more likely in their contexts. In the verified CPU run on this machine, validation loss moved from 3.7435 to 0.2038 over 2000 steps. The run took about 45 seconds. Your runtime and exact decimals will vary with hardware and software versions. What matters is the trace. The manifest records the seed, dataset size, vocabulary, parameter count, training steps, best checkpoint, and final metrics. A number on screen is evidence only when we can reproduce where it came from. Lower loss tells us the model fit the data better. It does not yet tell us whether it learned broadly or simply copied, so evaluation comes next. The trained sample is dramatically more structured, but this is where an honest course must slow down. Our entire corpus contains only 40,805 characters. That is tiny. The evaluator searches each generated sample for its longest exact match in the training corpus. For the question prompt, it finds a long phrase beginning with a token ID as a measured quantity and continuing into the coach correction. In other words, the model did not merely invent a new explanation, it reproduced a span it had seen. That does not make the project useless. It makes the lesson better. We can see optimization working, and we can see why low validation loss on a narrow dataset does not prove broad intelligence. Training loss, validation loss, sample quality, and copying checks answer different questions. A serious evaluation keeps all of them. This Tiny GPT is a mechanism learning project. It is narrow, easy to overfit, and unsafe to describe as a reliable assistant. Seeing that boundary is part of understanding how models perform. We have reached the end of the build, so let us reconnect every step to the promise from the introduction. Let us summarize the journey. We began with text and converted every supported character into a token ID. We shifted the targets by one position, so every context asks what comes next. We trained a bigram baseline and learned that one character of context is not enough. Causal attention then allowed each position to use earlier information without seeing the future answer. Token and position embeddings, 3 transformer blocks, and a language model head turned those pieces into Tiny GPT. During training, predictions produced loss, loss produced gradients, and the optimizer updated every weight. Finally, we compared fixed condition samples and checked copied spans so improvement did not become an exaggerated claim. The result is not one lucky sentence. It is a working model plus an inspectable chain of evidence. 12 tests, a baseline, a checkpoint, a training manifest, before and after generations, a copying check, and a model card. Return to the finish line from the introduction. Can you trace text to tokens, tokens to logits, logistic to loss, loss to gradients, updated weights to generated text, and generated text to honest evaluation? If you can explain that loop, you now understand the mechanism this project was designed to teach. I'm preparing a guided course called Build Your First Tiny GPT from Scratch. It is approximately 3 hours and follows one continuous Python project from an empty model to measured training evidence. You will not call a model API and you will not download pre-trained weights. You will write and run the code with me, use 2 small interactive labs to make token shifting and causal attention visible, and finish with a model card and a controlled experiment. You need basic Python, curiosity, and a laptop. You do not need prior machine learning experience. Join early access only if you want to do the work, inspect the evidence, and understand what every major part is doing. The link is below. Build the smallest real version first. Once you can trace that system end to end, larger language models stop looking like magic and start looking like engineering. If this helped you understand the topic in simple terms, follow or subscribe to In Simple Terms with Satish and share this episode with one friend who likes technology.